Welcome back. So now we would continue from where we left in the last video. So we have represented our signal in the signal space into a signal into the vector space. So if we have a set S containing S1 of t, S2 of t, all the way to Sm of t, which are the m possible signals that you want to transmit uh, for a memory modulation, then you can write those signals in the form of vectors s1 vector, s2 vector, all the way to sm vector, where each of these vectors, say si, can be represented as summation j equals 1 to n sij phi j, where Sij is nothing but the projection of the signal Si of t onto the basis function phi j of t. So this Sij can be represented as integral from 0 to capital T Si of t phi j of t dt. So now suppose you have an AWGN channel. That means you transmit the signal Si of t and into an AWGN channel. That means a noise, white Gaussian noise, gets added and you receive signal R of t, which is nothing but Si of t plus n of t. So remember, your Si of t is nothing but summation j equals 1 to capital N Sij times phi j of t. In a very similar manner, you can compute what are the projection of the signal n of t. So you can compute the projection of the signal n of t onto, there's a considerable lag here. I have to restart here. Yeah. So you can represent, you can find out what are the projection of this signal n of t onto the basis function phi j of t. That means you can represent the noise part as well by the projection onto the basis function phi j of t. It would be summation j equals 1 to capital N nj plus times phi j of t, where this quantity j is nothing but the projection of the noise n of t onto the basis function j of t. We can assume that these basis functions span the set S, but it would be a very hard assumption if we assume that these basis functions also span the noise n of t. So it is, for most of the text, what we allow something which is called nr of t, which is called the remainder noise. So nj of t times phi j of t summation j equals 1 to capital N would be the contribution of the noise onto the basis function phi j. Plus there would be some noise that would be orthogonal to the signal space. So because of this property that this noise, remainder noise, would be orthogonal to this signal space, this noise is typically ignored because the projection of this remainder noise onto the basis functions is typically zero. And hence this would be ignored. So under such a scenario, you can also represent your received signal R as summation j equals 1 to capital N Sij plus Nj times phi j of t, and you can call this quantity Rj, where Rj would be nothing but the projection of the received signal R of t onto the basis function phi j. So this Rj would be integral from 0 to capital T. Your received signal R of t phi j of t dt, and hence your received signal can also be represented as an n-dimensional vector. So you can call this R to be equals to R1, R2, R capital N transpose. This would be an n-dimensional vector like these vectors S1, S2, all of these vectors are n-dimensional vectors comprising of the projection of these signals onto the basis function phi j. Similarly, these components R1, R2, all the way to Rn are nothing but the projection of the signal R of t onto the basis function phi j. So you have this received signal R of t as a represented as a vector as well. So now let's talk about what would be the PDF or the distribution of the received signal given a constellation point Si.